Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on basic control systems for mechanical engineers, and I am Dr. Keval Ramani with I am faculty here with the Department of Mechanical Engineering, and as a part of this course this course will be divided over 10 lectures. We are going to start with linear systems and Laplace transforms in this lecture. In the next lecture, we will focus on transfer functions. Then that will be followed in the third lecture by block diagrams and time domain specifications. In the fourth lecture, we will focus on stability. In the fifth lecture, we will focus on PID control. In the sixth lecture, we will focus on root locus. Lecture 7 will do lead lag compensation. Lecture 8 will do Bode plots. Lecture 9 will focus on Nyquist plots, and finally we will wrap up with lecture 10 with state space equations. So for today we will start with linear time invariant systems, or rather LTI systems. So here there are two parts. One is linear systems and the other is time invariant systems. So first we will start with linear systems. So say we are given a system and for an input signal u1t we get an output signal y1t. Similarly, if we give another input u2t, which gives an output y2, then this system is linear if it follows the concept of superposition. That is, if we multiply the first input by a constant C1 and we add it to C2, that is multiply the second input by C2 and we add both of these C1 U1 plus C2 U2, then and apply this to the system, then what we should get is the output should be multiplied in the same manner. So we should get output signal as C1 Y1 plus C2 Y2. And if a system follows this, then it is called a linear system. So let us look at an example. So let us consider that we apply some input ut and the definition of system is this output yt will be u times sine omega t, where omega is some constant, t is time. So, the question is this system linear? So, towards understanding that, what we will do is we will apply this kind of an input C1 U1 plus C2 U2 to the system. And we will try to understand what is the output. So, what we see, what we will do in place of at the output side where there is u of t, we will substitute this particular expression C1 U1 of t plus C2 U2 of t. So, based on that, what we get is C1 U1 of t plus C2 U2 of t. The whole thing will be multiplied by sin omega t. So, let us denote this as some a. Now, what we will do, we will try to find this particular expression, that is C1 y1 of t plus C2 y2 of t, and that particular expression what we get is C1 u1 of t sin omega t plus C2 u2 of t sin omega t. So, we can pull out this particular expression part to get So, based on this we get this second expression. So, let us denote this as B. So, what we see is A and B are identical. So, this system is linear. So, now we have done the part where we saw we have looked at the linear part of the system. Now, let us focus on the time invariant part of the system. So, let us come back to our system which has an input u of t and our output is y of t. So, this system can be called time invariant if say u of t gives an output y of t, then u t minus t naught, where t naught is some constant, should give y t minus t naught. So, the whole idea is there is a time shift here at the input. You should get the same time shift with the output and both the signals should be equal. So, let us consider an example. So, say we have a system defined as y1 of t So, this is basically y dot implies its derivative of y with respect to time t, and plus k into y1 of t is equal to u1 of t. This u1 is the input, y1 is the output. Now let us say that for this system I will apply the same input, but there will be a shift in time of tau. So, the time will be t minus tau, and corresponding to that I will get some output y2. So, our question is, for this to be time invariant, basically the question which we'll have to answer is whether we can get y2 of t is equal to y1 of t minus tau. So, this is our question. So, what we will do is we will assume that this holds true and see how this works out. So, once we make this assumption, we will substitute it back into this particular equation. So, based on that, what we get is derivative of y1 with respect to time t minus tau plus k y1 of t minus tau is equal to u1 t minus tau. Now, let t minus tau is equal to some neta, and this concept is what we call is the change of variables. So, if we do this, we get derivative of y1 dot with respect to eta k y1 eta plus u1. So, if we see this particular expression, say we denote this one what we had earlier as c and this one as t, we find that both c and d are same, just we have changed the variable from t to neta. So, since they are identical, we can conclude system is time invariant. Now, for this example, what if we changed this k to be a function of time? For example, this particular k is a function of time. In that case, this time invariance won't hold, and this will be a time varying system. So, now let us go back. So, we have studied linear system and time invariant system, and when both these properties are present in the system, we call it a linear time invariant system, or rather an LTI system. This course we are going to focus on these LTI systems. So, now that we have studied the concept of linear time invariant systems, we are going to next focus on what is called the Laplace transform. So, the Laplace transform denoted by this particular symbol of a time domain signal f of t can be expressed as a function of a complex variable s called the Laplace variable and is denoted as f of s and given by this particular integral that is f of t into e to the power minus st dt going from negative infinity to positive infinity, and this s is the Laplace variable is a complex number denoted as s is equal to sigma plus j omega. So, the whole idea is we are taking a time domain function f of t and converting it into a frequency domain function f of s. So, now if you look at this particular part, that is e to the power minus st, you will find it's e to the power minus sigma t is one part of that into e to the power minus j omega t. So, this is the exponential part and this is a complex sinusoid. Now, this integral goes from negative infinity to positive infinity, whereas and sometimes this integral might not be defined. So, one way what we can look at is we just take the limit from 0 to infinity. So, f of s goes from 0 to infinity f of t e to the power minus st dt. So, this is basically a one sided Laplace transform. Why do we do one sided Laplace transform? The reason for that is most of the control signals you will see, such as f of t is equal to 0 for t less than 0. So, that's the reason we just go for in integration, we go from 0 to infinity. So, we just use a one sided Laplace transform in control systems. And why we have f of t is equal to 0 for t less than 0 is most of the physically realizable systems are basically causal in nature. That is, they only look, the output only depends on the past outputs and inputs. It does not depend on the future inputs. So, this was about what we discussed about Laplace transforms, how to get the Laplace transform given. So, we found how to get f of s given f of t. Now, we will look at inverse Laplace transform. So, what we earlier did was given f of t, we found f of s. Now, what the inverse Laplace transform does is given f of s, find f of t. So, this is given f of t is equal to 1 by 2 pi j integral of f of s e to the power s t ds, and the integration limits go from sigma c minus j omega to sigma c plus j omega. Now, in practice this is typically not used. Instead, what we do is we use one is properties of Laplace transform, and two, we use tables for standard functions. So, here I will show you this particular table lists down the different properties for Laplace transform. So, the first property is, say I have two signals f1 whose Laplace transform is f1 of s, and another signal here. So, Laplace transform of f1 of t is f1 of s, and the Laplace transform of f2 of t is f2 of s, and say I superpose this time domain signal to be alpha 1 f1 t plus beta alpha 2 t, then I get the corresponding Laplace transform is alpha f1 of s plus beta f2 of s, and the same applies if I do this superposition in the Laplace domain, then I get a superposed signal in the time domain. The next property is, say there is a time delay in my time domain signal, that is it delayed by a quantity of lambda, then in the Laplace domain my Laplace transform function for the original f of t, that is f of s, will be multiplied by e to the power minus s lambda. The next property is about time scaling. So, if my time domain signal, instead of time t I have f a into t, then my corresponding Laplace transform will be 1 by mod a multiplied by f, which is a function of s divided by a. So, if I scale it in the time domain multiplied by a in the Laplace domain, it will be divided by a in the Laplace variable, and there will be a mod division by mod a. Say I have a shift in frequency where I add a variable s plus a, then correspondingly in the time domain I will get f of t, but that will be multiplied by an exponent e to the power minus a t. Now, the most important property which we will see is what happens when I differentiate a time domain signal, what will be the corresponding Laplace transform. So, what you see is, if I take the mth derivative, it gets multiplied by the Laplace corresponding Laplace transform will be multiplied by s to the power m, and similarly then there will be other factors s to the power m minus 1 and so on, which will be multiplied by the corresponding initial conditions on the derivatives as well. So, here it is f0, then s to the power m minus 2 is multiplied by the first derivative of f at time t is equal to 0. So, for example, if I want to just find the Laplace transform corresponding to the first derivative of f1 of t, by this formula it will be s to the power 1 f of s minus f of 0. So, that is about differentiation. The next part is about integration. So, if I integrate the time domain signal, then the corresponding Laplace transform will be 1 by s into f of s. Then the next most important property is about convolution. So, what we know is say we have a signal and a system, and the corresponding is the output will be given by the convolution of the two. In that case, the convolution in the time domain. So, the corresponding Laplace transform is basically just a multiplication of the two Laplace transform corresponding to f1 and f2. So, basically convolution in the time domain is basically multiplication in the Laplace domain, which is very useful in mathematical representations of control system. The next one is the initial value and the final value. So, the initial value of the time domain function f of 0 is basically limit as s tends to infinity s into f of s. So, all I need to do is take s into f of s and takes its limit at s tends to infinity. The next one is the final value theorem, which is as time t tends to infinity, what happens to the value of the function f. So, for that, if I am just given the Laplace transform, all I have to do is take s into f of s and set the limit s tends to 0. And then you have other properties such as time domain, then Parseval's theorem and multiplication by time. Now, based on these properties and some, we can easily derive what is the Laplace transforms for simple time domain functions. So, for example, if we say f of t is basically 1 for t greater than or equal to 0 and 0 as t is less than 0, then we can just substitute in that particular expression. So, going from 0 to infinity, f of t will be 1, we will get e to the power minus s t dt, and if you perform all these calculations, you will see that it is just 1 by s. And you see the same thing here. So, this 1 of t basically denotes this definition, that for t greater than or equal to 0 it is 1, and for t less than 0 it is 0. So, for this 1 of t you get the Laplace transform is 1 by s. Similarly, for other you can take this simple integral definition and based on that get the Laplace transforms for these different time domain functions, and then we can use these Laplace transforms to find Laplace transforms for other more complicated time domain functions. So, now we have seen what are the properties of Laplace transforms and how we can just use this definition here to find Laplace transforms for simple functions, and then we can use the Laplace transforms which we have developed for simple functions in this table to find Laplace transforms for more complicated functions. We will do a couple of examples on how we can go about that. So, the first example, so say we have this particular function in the Laplace domain, and we want to find what is the corresponding f of t. So, we could break this down using the concept of partial fractions. This will be, so So we can find this as so once we have this expression, what we do is we go to our table. So if you look at this entry number 7, what you will see, it's 1 by s plus a is basically e to the power minus 80. So let me just write it down here. So 1 by s plus a is e to the power minus 80. So if we look at the first expression, what we get, in this case a will be 2. So we get e to the power minus 2t. Similarly here, for this particular expression, a will be 3. So e to the power minus 3t. So this is our time domain signal f of t for this Laplace variable function f of s. So this was our first example. Now let's look at another example. So say we have f of s plus 1 divided by s square plus 4s plus 30. So let us just focus on just this particular denominator. So if we now go to our Laplace transform table and just look at this particular denominator, what you see is that it will correspond very closely with this particular part here, 20 and 19, that is s plus a the whole square plus b square. So basically if we look at this particular denominator, we can express s square plus 4s plus 13 is equal to s plus 2 the whole square plus 3 square. So this is now in the form of s plus a the whole square plus b square, where a is 2, b is 3, and the corresponding here, if you look at 19, this is basically s plus a divided by s plus a the whole square plus b square, and corresponds to e to the power minus 80 cos bt. Similarly, if we have just a constant in the numerator, b divided by s plus a the whole square plus b square, we get e to the power minus 80 sin bt. So based on this, we can take this f of s and expresses in this form. So now if you look, we have s plus a, because our a is equal to 2 here in this part, and this is the numerator here is constant, and ideally we would like it to be equal to b. So what we will do is, since b is 3, we will just divide here by 3, and based on this particular portion, the corresponding f of t is e to the power minus 2t cos 3t, and the other part will be minus 1 by 3 e to the power minus 2t sin 3t. So this is our time domain representation f of t for this particular Laplace function f of s. Now, in the next part, next example, we are going to focus on how we can solve ODEs using this portion. So, for doing that, what we do is, let us take one example, y double dot, that is double differentiation of y with respect to time t, times 3 y dot t plus 2 y of t is equal to 0. So, this is our ordinary differential equation with the initial conditions y 0 is equal to 1 and y dot 0 is equal to 3. Here we have two initial conditions because this is a second order equation. So, we know if we denote the Laplace transform of y of t as y of s, then the Laplace transform of y dot of t is s y of s minus 1 and y double dot t will be s square y of s minus s minus 3. So, now that we have this Laplace, we have listed down the Laplace transform, we can substitute in place of these y these Laplace transform variables. So, basically we will get s square y of s minus s minus 3 plus 3 s y of s minus 3 plus 2 y of s is equal to 0, and this can be written as s square so based on this we can get and then we can use partial fractions as done in the previous examples to get and then we can go back to the table entry number 7, which gives 1 by s plus a, the corresponding time domain function will be okay. Now, we have solved this using Laplace transform. So, now we can do this something about this also in something like software package like Simulink. So, how do we represent this equation? Using a block diagram. So, let us say, let us denote x1 of, this is basically x1 of t is equal to y of t, and we have x2 of t is equal to y dot of t, that is the first derivative. So, basically from this what we will get is x1 of x1 dot of t will be y dot of t, and that is equal to x2 of t. Then the other condition will be, the other equation is x2 of t which is y double dot t here plus 3 x 2 of t plus 2 x 1 of t. That is, what we are doing here is basically we are substituting these two equations definitions in this particular equation. So, based on that we get is equal to 0, and our initial conditions, which were y of 0 is equal to 1 and y dot of 0 is equal to 3 basically. So, for this particular equation, what we will get is for y of 0, since it corresponds to x 1. So, x 1 is 1 and y dot implies x 2 of 0 is equal to 3. So, based on this we can draw a block diagram. So, the outputs of this block diagram will be basically x 1 and x 2 . So, if we want to integrate, okay, so our outputs are x 1 and x 2 and we will get them by integration. So, to get x 1 will basically take x 2 and integrate, and this is based on this particular equation. Now, coming to the other equation, if we want to get x 2 so what we will do is we need to integrate this particular expression. So, we will take basically here we will have a summation block. So, we will take minus 3 x 2 here, and similarly we have minus 2 x 2 x 1 . So, we will add them up, and here we will get minus 3 x 2 minus 2 x 1, and this will be integrated to give us x 2. Now, these initial conditions will be embedded within these integration blocks. So, here we will have the initial condition for x 2 and here we will have the initial condition for x 1, and in this way we can implement this on Simulink and find the answer, and we will get something, and we will get an identical expression done here. So, I leave that as an exercise for you to try out. So, now with the understanding of the Laplace transform, we will move to the final concept for today, that is called the final value theorem. So, the idea about final value theorem is if all poles of S y of S are in left half plane of the S plane, then the limit t tends to infinity y of t is equal to limit s tends to 0 as y of s. So, LHP implies left half plane, And poles are basically, say we have any Laplace transform, say we could express, say this particular, so we could express this signal y of s as some numerator polynomial y1 of s and y d of s. So, there is a numerator polynomial and a denominator polynomial. So, the roots of this denominator are called the poles, and here we have for the numerator the roots are called the zeros. So, for final value theorem, what we will do, if we want to find what happens to the limit as t tends to infinity for y of t, we will consider s y of s, find such pole. If they are in the left half plane, we can implement the final value theorem, which says that as t tends to infinity for y of t, the value will be equal to limit of s y of s as s tends to 0. So, let us look at one example. So, now for this particular expression, what we will see is if we check s y of s, it is basically equal to so what you will see is we get s square plus 4s plus 11 has poles which are in the left half plane, because this can be easily be expressed as so since there is a s plus 2 the whole square, the real part will be minus 2. So, based on this we can apply the final value theorem and we will get as limit t tends to infinity y of t will be equal to s tends to 0 for this particular expression. So, we will get this as the final value. Let us look at another example. Now, if you look at this example, what you will see is if we look at the poles, there is one pole which is not which has a positive real part. So, it will lie in the right half plane basically. So, based on this what we so we get this expression for y of s. So, corresponding expression for y of t will be from the Laplace tables. So, if you see as t tends to infinity, this function here will be basically unbounded. So, basically as limit t tends to infinity for y of t, the signal will keep on growing and the final value theorem will tell us that the limit tends to infinity or keeps on growing unbounded. So, with that we will end today's lecture, where we focused on linear time invariant systems, Laplace transforms, and finally final value theorem. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. I am going to discuss a question which is frequently posed to sociologists, and that is, what is the role of sociology in policy making. Now, so far in our country and also in the world, in World Bank, in UN organizations, in Population Council, planning is seen as something for which economists are particularly trained, and very few sociologists were found in planning process. Planning was given to statisticians and to economists. But now gradually planners and states are realizing that sociologists have a very important contribution to make to planning process. What can sociologists do to planning? Sociologists can pose problems. Sociology can identify which problems of society need priority or greater intervention. Like Indian society may be suffering from thousands of problems, but since solution of problem requires expenditure of resources in terms of time, money and manpower, all the problems cannot be solved, or we cannot focus on all the problems. Do you know that our national health plan focuses only on 15% of the diseases from which people in India die? It is not possible to cover all 100% diseases in the program. Program means resources. So, sociologists can help us by conducting surveys, by talking to people, by doing field work, that from people's perspective which problems need to be given greater attention. Then sociologists can also help the planners in understanding various dimensions of the problem. Suppose you are trying to solve the problem of why in India maternal mortality rate is high. We know that maternal mortality rate means rate of deaths among women associated with childbirth is particularly high. Sociologists tell them that this problem is not going to be solved simply through health intervention. We have to look at things in entirety or totality, or what we call holistically, and we have to understand that India has a patriarchal system in which in rural areas particularly value of life of a woman is very little. This is one meaning of patriarchy. So, if you do not care about your women, you will not take them to health center also. There is a problem of transportation, there is a problem of ignorance. People do not know the danger signs, people do not go to ashas, people do not go for ANC, people do not understand the danger signs. There are several danger signs which everybody should be able to know if a woman in the family becomes pregnant. Sociologists tell that apart from health interventions, you require other interventions also: education, empowerment, power of women in decision making, nutrition, control of stress. The sociologists can tell the planners all these. And one important role that sociologists can play in planning process is by involving in monitoring and evaluation of development programs. From time to time government launches various programs for the benefit of people, like you all have heard about Manrega, Mahatma Gandhi National Rural Employment Scheme or Act. Manrega, A for Act as scheme, or other welfare programs. We sociologists can conduct studies and tell to what extent goals of these programs have been attained and what are the bottlenecks or what needs to be done in the future to improve the effectiveness and efficiency. Effectiveness means reach, efficiency means cost benefit ratio, how to improve effectiveness and efficiency of the program. And are there some specific groups where some specific intervention is to be launched to make these programs successful. Something which can work in Delhi may not work in remote tribal areas of Chhattisgarh. So, sociologists help the planners in evolving area specific approach to implementation of their development programs. These days an interesting branch of sociology called reflexive sociology can also help the planners in understanding if the methods that they are using to solve the existing problems, they are themselves going to create new kinds of problems in the future. Reflexive sociology is about understanding the ill consequences of interventions launched by the government or NGOs or by civil society in the interest of society. You know, something which we do for improvement or in the interest of society can also create problems. Bureaucracy, for example, created the problem of red tapeism, and health programs led to population crisis, urbanization led to alienation, and development produced the environmental problem. So, reflexive sociology can help you in anticipating if your solutions are going to create new problems and how to deal with them. Thank you.